if you learn the higher level, if you go higher and higher level in theoretical mechanics, right, if you learn about more like graduate level theoretical mechanics, you will come across Hamiltonian and something that looks similar to the commutator that we just saw on the previous class. And that, in that sense, actually quantum mechanics is not very far from theoretical mechanics. You just do one small change, the h bar come out. But actually what we are doing now is a lot of it come from advanced theoretical classical mechanics. So, but yeah, I guess it's something to worry for you guys to worry in the far future. Maybe some of you, depending on what research area you focus on, you might not even deal with this at all. But what we will be doing today, we should probably get started now, is to begin chapter 2. So we spent quite like a long time going through the basic postulates of quantum mechanics, right? And we learned how to manipulate vectors in Hilbert space. We talked about operators. We learned how to calculate probabilities and expectation values and all those things. That might feel a little bit boring, but it's like, you know, it's something we need to get through first. Then once we develop all these tools, we have built up all these methods and tools already, then we can start solving some simple system, which is what we begin with in chapter 2. So chapter 2 is basically covering two simple experiments, relatively simple experiments. So this one is done, I think, in the early 1920s, and this experiment is done in around the 60s. Did I press record? Test, yes. Yes. Okay, so yeah, so when we talk, so these are the two experiments developed in the early quantum mechanics. So there's what we will start today by talking about the Stern-Gerlach experiment. There's a lot of interesting history behind this experiment as well, and so this is another experiment that demonstrates the quantization. Okay, because in other earlier courses, there are other experiments that taught you that not taught you guys, but taught the earlier physicists at the time about things in small scale. They do not behave the same way as classical mechanics. Okay, so the black body radiation, the photoelectric effect, what was the other one? Compton scattering, right? So those were the three experiments that shows the early hints of quantum mechanics. And then in week 1 lecture, we talked about the electron interference as well. So that is another experiment that start to introduce quantum mechanics to us, and that is also why we cannot use classical mechanics. We need to use wave functions and things like that. And then now this is another one. So let's talk about the Stern-Gerlach experiment. Okay, so this is section 2.1, right? So let's get started by the Stern-Gerlach experiment. So it's two scientists, somebody named Stern and Gerlach. Okay, so the basic setup is like this. So let's talk about the basic setup first, and then so we introduce the basic concept of Stern-Gerlach experiment, and then later, like probably the end of this class or next week, we make the experiment more and more complicated. And it's kind of, this is like a prototype of what is going to be called quantum circuits, which is another interesting cool things that is being researched today. So let's start. We have to understand the basics first. So basic setup, right? So what's the Stern-Gerlach experiment about? So this one is something we have covered only like very briefly. I think only like mentioned for like 5 minutes in the electromagnetism course. So the MAT students who did not take it, don't worry. The base is, I will just say this again, but we are talking about this in terms of quantum mechanics. So what I'm talking about here is the dipole moment, right? So if I have a wire, and then I make it to go into a loop going with a current I, right? So there's a current loop, and then if I have the area A, what's going to happen, right? So if I have a wire going in a closed loop, when there's current running through it, it's going to create a magnetic field, right? So the magnetic field will be something like this, right? Something with some shape, but actually this magnetic field created by this current is not important. What is more important to us for today is the dipole moment. Okay, so if my current is I and this is A, we define the magnetic dipole moment. Right, we call this mu. Okay, it's a vector mu and is defined by the magnitude of the current and how big is this area, and then the direction of this using the right hand rule. Okay, so this is the magnetic dipole moment if we are talking about the current loop. So this is just using current loops, right? So what we did last time, which is not what we're doing today. What we're doing today is to study the dipole moment of atoms. So atoms also has a dipole moment. Okay, so atoms are particles, right? And you cannot make this into a wire, but it has something similar. So atoms, I'll just draw this atom as a sphere, right? So as a sphere, and then it has some charge and things like that, and it will be behaving in such a way that it can also has a dipole moment. Okay, so atoms also has atoms also carry a magnetic dipole moment. Okay, so let me write it down here. Also carry its own dipole moment, magnetic dipole moment. Okay, so let's just call this vector mu because it is some vector, so it's going to be having some direction and some magnitude. And the magnitude you can just imagine like, okay, the higher the charge, the faster it spins, then the higher the magnitude. That is a very rough model to imagine what the atom looks like. But as we go deeper and deeper into quantum mechanics, this picture is no longer accurate. But at least at this level, it gives us something to imagine, right? So there is some magnetic dipole moment. So before it becomes too abstract, right? Dipole moment is actually something like very straightforward. Let's say like it's like a north-south magnet, and then we got the dipole moment of a north-south magnet is like this, right? The magnetic field is something like this. So you can imagine atoms as little tiny magnets with north and south pole that is too small. They are almost the same point, but it has a direction. Okay, so it has a direction and it has a magnitude. It will tell me how strong the magnet is, right? So in quotes, because they are not real magnets, they are particles, but they create magnetic fields in kind of the similar way. Okay, so that is the essence of the Stern-Gerlach experiment, is to measure this magnetic dipole moment, right? So that is the original design of the Stern-Gerlach experiment. So the Stern-Gerlach experiment, so this is a very long thing to write, so I'll just call this SG. Experiment is to measure the magnetic dipole moments, and I think for the original experiment is to measure the silver atoms, right? Because different atoms will have different dipole moments. So what they used in that experiment is silver atoms. Okay, so silver atoms, yeah, it will have some charge, right? Because they have a certain atomic number, which I don't remember, but it's not important. What is important is this vector mu over here. Okay, so what does the experiment looks like? Okay, so I have drawn the nice looking diagram in the lecture notes already, but roughly speaking, you need to have a source of silver atoms. So the schematic diagram calls this an oven, and it's because you have some sample, probably a block of silver, and then you put it in some oven to heat it up, and then some of the atom particles will start to release in the air, and then you let it escape through a hole here, right? So you got some silver atoms source, right? And then it will come out, right? So it will come out as a beam. So it's not just a single atom at a time. Generally, there are multiple atoms, right? So it's a beam of atoms, many particles all flowing out through the coming out from the gap here. And then to detect the dipole moment, right, what we want is an inhomogeneous magnetic field. So is this Toblerone biscuit shaped thing here and a cube box thing here. Okay, so it will gonna pass through here, and this is like two ends of a north-south magnet. So this this south pole of the magnet has a very weird shape because we want to create an inhomogeneous magnetic field. Okay, why inhomogeneous? I will show you later, but the main point is, okay, if it's inhomogeneous, then it will exert a force on this atom, right? So it's gonna push the atom, and I will show you later the value of the force depends on this magnetic dipole moment, the value and the direction of the force. So the atoms will be different atoms of different dipole moments will get pushed in different forces. So one might go up, other might go down. Maybe could it go to the center? I don't know, right? I will show you the experiment later, but the design is you have a screen that collects the atoms here. Okay, so let's put this as my z-axis, and the z equals to 0 is the center over here. Okay, so maybe the screen is to see how many atoms go in the positive z direction, how many atoms go in the negative z direction, or anywhere in between. Okay, so that is the basic setup of the Stern-Gerlach experiment. Now, so the next thing to address is why do we want inhomogeneous magnetic field? So let me show you what goes on, right, for an inhomogeneous magnetic field. So let's draw my south pole of my magnet like this, and then the north pole of my magnet is like this. So the magnetic field it creates is going to be something like this, roughly speaking, right? So they make it this shape so that the magnetic field is concentrated on the upper side, right? And then on the bottom side is more spread out, so it's inhomogeneous. Okay, so what happens here is that for in the region of the higher side, so at positive z, the magnetic field is stronger, right? So this is z equals to 0, and then for negative z, the magnetic field is, see, the field lines are more far away, it is a weaker magnetic field. Okay, so just now I was saying that the silver atoms have a magnetic dipole moment mu, right? I explained this just now. So this will interact with the magnetic field, right? If you put a magnet inside another magnetic field, the magnet will experience a force, right? Magnet and magnet will get attracted or repulsed. It depends on the direction. Okay, so in so yeah, this is just a statement to remind you, but inside a region of some magnetic field B, right? So in a region of magnetic field B, okay, it's going to experience a potential energy. So the potential energy of the particle of the atom is given by this formula. So it's mu dot B. Okay, so this is the potential energy, and we have this was in theoretical mechanics or in classical mechanics, but even if you're not learning this, never mind, I'm telling you this now. The force on the particle on atom is the gradient of U. So F is in fact is the negative gradient of U. Okay, so negative gradient of U means negative negative, so it's just the gradient of mu dot B, right? So mu dot B is a scalar number, but it's a function of Z because B is inhomogeneous. It depends on Z. So it depends on Z. So if you take the derivative, it will tell you the direction of the force. Okay, so this is just to show people something familiar for those who have seen. If for those who are not familiar, it's not important. The important point is, because of this equation, atoms generally, yeah, because this is the Newton's law, atoms will get pushed. The force is a pushing direction, right? So it will be pushed towards the region or domain, towards the region of low, just low potential energy, right? So so potential energy depends on Z, okay? It depends on the direction of mu, it depends on the direction of B, but in any case, whatever this is, right, there's going to be somewhere with high potential and somewhere with low potential. I will show you exactly where later, but because of this Newton's law, yeah, let's call this Newton's law. Well, because of the force, right, generally force will push objects to a region of low potential. Okay, so all we need to know for this course is, in fact, we will deal with potential energy a lot in other places. Generally speaking, the particle will get pushed towards somewhere with a low potential. Okay, so before I go to the next thing, does anyone have any question? Prof Ong also got mentioned SG experiment. Okay, so when you bend the bike, you cause the force. That is true, but I think I don't know whether people has worked out the details yet or not. I can't know that. Okay, so we have labs, but it's not tied to the quantum mechanics course. Yes. So it's kind of similar to where each atom has more dense electron. So we will actually discuss this when we talk about the maser. It will play a part in the maser later. But now we are not talking about electrons. We are talking about the entire bunch of atoms themselves. Yes, but also true, right? A bunch of atoms themselves. But if before people know quantum mechanics, if we treat them like particles, then each particle will experience a force. So yes, in that way, it's kind of the same thing. Okay. Now you want to eat chocolate? Actually, me too. Yes, we are refreshing EM things. Well, not really. Well, it's kind of both lah, right? We are bridging the gap, and the real QM-ness that you see in this course is after this part. We will this part, Prof Ong mentioned this a little bit, and I'm mentioning some of this again. And in fact, you are refreshing EM course again. But the main point of this course, we will use the bra-ket to understand this situation. Okay. So let's see who or what region has the lower potential energy. It depends on mu, because mu can be positive or negative. So let's take some example. Let's study them case by case, because whether the function is a positive or negative number, right, it depends whether mu is parallel to B or opposite to B. Right? If it's opposite, the dot product is negative, you get a positive function. Okay, then who is high, who is low, it changes. If mu is a negative, then it changes as well. So we need to, the best way I think to understand this is just to look in case by case. So let's say my atom has my magnetic dipole moment is pointing this way. Okay, so let's see what happens here. So my atom, my inhomogeneous magnetic field is like this. Yeah. Okay, so this is the middle part. Right, so the middle part, like I said, is the magnetic field is stronger, but what about the function? It depends, right? So if B is pointing this way, and generally the magnetic field are pointing upwards, so mu dot B is a negative number. So in this case, U is negative mu dot B, right? They are same direction and then negative, so it becomes a negative number. Okay, so then now we check who has a higher value. Well, mu is a fixed scale. The length of mu is fixed, right? We already took care of the direction, but let's look at the size of this function. So just now we said that for Z positive, the B is stronger, right? So if B is stronger, what happened to the U? U is a larger magnitude but negative, so U is very negative. Okay, but on this side, on negative Z, then my magnetic field is weaker than above. So if this is a weaker number, then U is a negative number but less negative, is closer to 0. So U is less negative. Okay, so now I have reminded you that force will get pushed to a region of low potential. Where will the particle go if the spin is pointing up? Can you guess? Right? It will get pushed to a region of lower potential. So the force on the particle in this case is upwards. Okay? Agree, right? So in this case, the force on the particle is upwards because this part is where it has the lower potential energy. Okay? Then of course, if I change the angle a little bit, right, it's still a negative function, but the mu, well, mu dot B will be a smaller number, but it will get pushed upwards but with a smaller magnitude. Okay, then if it is exactly perpendicular to my magnetic field, right, passing through my beam is shooting through the center. Okay, so my beam is shooting through the center. Then if this is the case, then U is mu dot B. If these two are parallel, right, so my magnetic field is upwards, is 90 degrees to this, so mu dot B is 0. Okay, so the force in this case is 0, right? Then yeah, so now you see the pattern. Now if we point it downwards, right, if pointed downwards, my potential energy mu dot B, because my magnetic field is pointing this way, so mu dot B is a negative number, another minus sign here, so mu dot B is positive, right? So what happens here? So here, okay, so here it is the opposite of what we said here, right? So it's a positive number, B is stronger up here, so it's a positive number and a strong number, so U is more positive. Right, then on down here, B is weaker, so U is less positive. Okay, so the particle will get pushed to a region of low potential energy. So where will it get pushed? Right, this part is lower potential energy, right? So this is low, for this case is lower potential energy was up here. So in this case, the force on the atom is down. Okay, so as you can see, right, for the direction of my magnetic moment, okay, from here to here to here to here to here, right, it depends on we can figure out what is the force and we can figure out what is the direction. So from here to 90 degrees, the force is generally to the upwards direction, and from here downwards, the force is generally to the downwards direction. So everything I have been talking about, right, yeah, you guys said that it feels like refreshing EM, is because this is not the quantum mechanics picture. This was back when people didn't really understand quantum mechanics yet. We are still using the knowledge that atoms are classical particles, right? So when Stern and Gerlach designed the experiment, they have some expectation. If we have this traditional model of the atom. So what we expect is that we do the Stern-Gerlach oven here, right, and then we shoot the beam through the magnet, right? We shoot through the center of the magnet. So what we expect is that the beam will spread, and then it will hit the screen over here, right? So you get a bunch of particles because of different directions, right? So what is the atom that goes the highest, right? The atom that goes the highest is the one that experiences the highest upward force. So to get the highest upward force, the dipole moment is pointing straight up, right? So slightly lower, then maybe is not purely vertically up, so it's like some direction, right? And then right in the middle is where the particle gets zero force, okay? And then the one that goes the bottommost is the one that experiences the largest downward force, the strongest downward force. That will happen if my mu is pointing straight down, and then the intermediate direction is over here, right? So that will spread out the magnetic dipole moments of all the different atoms. So it will sort the atoms according to dipole moment, okay? So this is what we expect, but I guess everyone knows the spoiler already, or the plot twist. When people actually did the experiment, this does not happen. Okay, when the experiment is actually performed. This does not happen. So that was another, I think by the 1920s, yeah, people already done the photoelectric effect and things like that. Okay, it's not that big of a surprise. They already like heard of the other experiments, but still this is another thing that was not expected before the knowledge of quantum mechanics. So what actually happens was it only splits into two beams, right? So you got the oven, and then you shoot this through inhomogeneous magnetic field, okay, and then what actually happens is you only spread into two beams, okay? So two beams, then we can say that this is only the atom pointing in this direction, and the magnetic moment is pointing in the downward direction. So the magnetic dipole moment is also quantized, right? So in the other early quantum experiment, the photoelectric experiment, let me write this down first before I forget. So the result of this experiment, we realized that it only split into two beams, two discrete beams. So the magnetic dipole moment of, well, at least for the silver atoms, but since then people can have done this for other atoms and other particles, it's true also, right? So for silver atoms is another example of quantization, okay? So this is the consequence of the Stern-Gerlach experiment, okay? Just like for historical context, we look at the black body radiation and the photoelectric radiation is that the photons are quantized, right? And for this experiment, we are talking about the spin, okay? And then if you look at the hydrogen spectrum, so that is also another experiment. The energy level, hydrogen spectrum tells us the energy levels, the energy of the hydrogen atoms are quantized. Now, we will actually solve this in this course, in chapter 4, but I think you're going to hate this because the math is going to be a bit messy. But these are all these phenomena that tell us, like, our normal description of particles is not consistent with observation, right? So this is why we spend so much time developing the Hilbert space, is because this doesn't work, so we need some new formulas and new math to handle this experimental outcomes. Okay, so yeah, so that is the main idea of the Stern-Gerlach experiment. So it's still pretty simple, right? I didn't use anything advanced. I'm just telling you that, yeah, it just split into two beams. So that's about it for now. Yes, correct. This is the spinning penguin, right? Yeah. Yeah, that's true. So yeah, so the electron, so the what you guys were talking about, like, for those of you who might be confused, is that I'm using the traditional model. Is that we call this the spin of the atom. Right? The spin of the atom is because we imagine atoms or electrons as spinning spheres, right? So that's why I draw this picture, right? It's some sphere and then it has spin. Once it has spin, it's going to have some axis of rotation, and because of this axis of rotation, a spinning charged sphere will have a magnetic dipole moment, right? So it has this, and it also has a magnetic dipole moment because electron carries charge, right? So electron carries charge, it will have this. Protons carry charge, it have this. But this is just the imagination. So I put this in quotes, right? So this is like we call this a very crude model. Okay, realistically, in real life, or realistically, it is a bit messy lah. So I'll just mention this a little bit just to clarify, but we will not worry ourselves too much, because the problem is electrons are literally points, are just points. Okay, so we cannot imagine the sphere because a sphere has some radius, but electrons are points. So how can a point spin? It can't. So it's just a point. But anyway, thanks to other calculations from quantum mechanics, it still has a spin and magnetic dipole moment. Okay, so the zero size is zero size, but still carries the dipole moment, and also carries angular momentum, and things like that. Okay, so I only say electrons because this is where it gets messy, and this is for later courses of particle physics. Protons and neutrons are finite size, yes, but they are made of 3 quarks. So we still can't take this picture anymore. It is a bit complicated. So so this is why, right? But for now, yeah, if we are not used to this picture, then we just think that, yeah, it's a spinning sphere, but we take the limit of the radius going to 0, but it still has some finite vector of dipole moment. Okay, so that is why. So that is where things get a bit interesting, right? Not to say complicated. If you just look at electrons, it's just from this picture to this picture. It's nothing, not that bad. Okay. The complication part is where we talk about quantum, the particle physics part. Like, yeah, protons are not points; they are made of 3 quarks. And how do you get this model? You need quantum field theory. And that is another graduate level problem. I also don't know. I've not learned particle physics, so it depends on whether you specialize on this or not. So what if the horizontal? Yes and no. So the answer to your question is we will come back to this in chapter 4. Yeah, chapter 4. Okay. So that is another complication. So we will come back to this in chapter 4. Yeah, you kind of like predicted already, right? So if you align your magnet like this, or if you align your magnet like this, right, and then you shoot the beam through here, how do you handle this? Well, it will still split into two. The simple answer is it will still split into two beams, but in this direction, right? So if you align your magnet in the z direction, it will split along the z direction. If you align in the y-axis, then it will split in the y direction. Okay. Then but this is talking about the different measurements, right? So we are focusing on the measurement along the z-axis, and this is focusing on measurement along the y-axis, and so on and so forth. And then you can try to do it for the z-axis as well. Okay. So yeah, simple answer, yes. It is same result but sideways, just to make a long story short. Okay, but we will definitely come back to this later. So now let us introduce the things that we learned, all the math that we learned last time, and we bring it to solve it here. So to begin, right, let us simplify the diagram. So let me simplify the experimental diagram, because every time I draw this triangle and things, it's very messy and takes wasting time. Okay, so we are still focusing on the z direction, right? And then we take the silver atom oven, so it will shoot atoms in the beam over here, right? And then this is what we call the magnet. And yeah, so just to have something to call it, a name to give it, we call it the SG magnet. Okay, so why did we learn operators, right? Remember what did postulate 3? Postulate 3 says that measuring a physical property corresponds to a Hermitian operator, right? What we are measuring is we are measuring this right? Because we are checking the experimental outcomes, like what comes out, right? So we are measuring this, and we are taking the z-axis. So we are measuring this along the z-axis, right? So this is a measurement. That means it should correspond to some Hermitian operator. Okay, so the Hermitian operator, I will call this sigma z. Z because we are talking about the z-axis. Okay, so the Hermitian operator is the sigma z, and what is the experimental outcomes, right? So should I? Yeah, let's just write this out. My sigma z is an operator. So let me tell you what is the matrix elements. Is 1 0 0 minus 1. Okay, so this is the operator, right? So now we start to see concrete things. We're connecting this to experiment, right? So why suddenly I give you this? Well, I will explain now. So the reason is because based on what happens here, we only have two outcomes. We have two outcomes, right? So measuring this should give you two outcomes, and that is giving me the two eigenstates of the measurement. Okay, so the particle that is going this way is one state. It is the state of having this axis, this dipole moment, and this is a second state of having this dipole moment, right? And what the postulate 1 says, state must be represented by a ket in Hilbert space. So this is the state of pointing up, this is the state of pointing down. Okay, so and with this state it corresponds to some eigenvalue, right? So what is the eigenvalue? Well, so the eigenvalue is the particle that goes up is having the positive z direction, so the eigenvalue will just say this positive 1, and the eigenvalue of this is negative 1, right? So we have all the things that we discussed in postulates 1 to 3, at least just 1 to 3 for the moment, right? So we got the operator, right? We got the eigenstates, and then we got the eigenvalue, right? So everything that we discussed last few classes comes into play like this. So hopefully you see now this is a concrete example, this is a real experiment, these are real outcomes, like the beam literally going up and the beam literally going down, and this corresponds to these two elements of Hilbert space, right? So if you just look at this when we discuss it, it feels very abstract, but now you see the connection to, at least something like the connection to reality or connection to this experiment. Okay, so the eigenstates, let me write this out explicitly. Okay, is 1 0, and the other eigenstate is 0 1. Okay, so then we can actually check these two are the correct eigenvalues. So let's check the eigenvalue equations. We have done this in the examples already, right? But now we are like really focusing on so it's worth doing this again, at least as a practice. Okay, so this times this gives you what? So this times this is 1 0 0 negative 1 times 1 0, so you just get 1 0 again. So basically you come back to the same vector as before, and this is just plus 1, right? So the eigenvalue for this is plus 1, right? And then you can also check the other state if it's pointing down, right? So if it's pointing down, we are still using the same operator. Okay, so it is 0 1. Okay, and then hang on, this times this 0 0 0, and this is negative 1, right? So this is actually negative of my original vector that I started with. So the eigenvalue of this state corresponds to negative 1. Okay, so see, plus 1 and negative 1. So so now we know what is this. Maybe the eigenvalue is still a little bit abstract, so let me just choose the coordinate system. So I'll just say that z is 1 here, z is negative 1 here, and this is the z equals to 0 line, right? So this is my coordinate system z. So this is why I can say that this is a plus 1 and minus 1. Okay, so it doesn't really matter at the moment. We just need something positive and we need something negative. And usually it's convenient to just make it plus or minus 1. Okay, so how do you feel so far, right? Is it a bit better from all the math that you learned last time, right? So much linear algebra, why is it quantum mechanics? Well, here it is, right? So hopefully it's a bit more clear and more satisfying to relate to having gone through vector and Hilbert spaces. Okay, so yeah. Oh, I forgot one thing. Okay, another thing that we talk about when we discuss about those postulates is that these are the measurement outcomes, right? But before you observe it, you don't know what outcome you will get, right? So that means before measurement, this is going to be some arbitrary state, right? So there's the state of the system. Okay, so it depends on what state that you prepare, but basically this is also the consequence of the postulate. When the atom is here, right, because the beam, if you don't disturb the beam, you don't know like what are the actual constituents of the beam. If you don't disturb it, this is before measurement. And then what happens is this is after measurement. Okay, so this is postulate 3. 3. So postulate 3 is, yeah, before measurement, it is some state, we don't know what it is, right? It could be a superposition, maybe it's already an eigenstate, we don't know. But after measurement, it is, the outcome is, the state of the atom is definitely up or definitely down. Before measurement, you don't know. Okay, this is the cat experiment all over again, right? Before you open the box, you don't know what the cat is doing. It could be dead or alive. You really don't know, right? But when you open the box, you only see dead or alive. You never see a superposition once you open it already. Once you observe, you can never observe a superposition, right? Because once you observe it, it becomes one of the definite eigenstates. Okay, so philosophically what it means, yeah, we don't know, right? We can't answer this. This is why quantum mechanics is difficult, because we still haven't figured out the answer yet. Before measurement, what is actually the atom doing, don't know. But the minute we try to figure out, you get one of these eigenstates, right? The observation destroys the superposition. Same like for the electron diffraction. If you check which slit the electron goes through, you destroy the interference pattern, because you make the electron go into one of these eigenstates. Same thing here, right? So this is the observation, right? It sounds abstract, observation represented by an operator, but it just means, yeah, if you pass the beam through this thing, it will either go here or here. So you get one of these two outcomes. Okay, so hopefully that makes sense. At least it makes sense to me. Any question? What time are we now? Wow, already. Okay. Yes, correct. Here the state is the spin. Yes. The eigenvalue and eigenvector is set by ourselves. Yes. So this is for a specific experiment, but yeah, you have because this is an experiment with two outcomes. So you got two eigenstates. That will give me a two-dimensional Hilbert space, right? And this. So it's not exactly 100% decided for yourself. For practical purposes, let's say it's given in the question paper in the exam, right? But later in the later chapters, we will dig a little bit deeper to derive why is it this matrix. Okay, so that will come in later. But for the moment, we just worry ourselves at this level first. So let's say this is given. Okay, so that is, at least it makes our life easier, because right now we just want to practice using bra-kets. Okay, simple stuff. So so that is what we worry about at the moment. Okay, so let's take an example of an arbitrary state. Okay, so let's say, right, my silver atom oven prepares atoms, right? It prepares atoms in the state. The oven prepares. Prepares also is the detail I will not discuss, but let's say I know the state will be given, right? So prepares atoms in the state. So let's say this is A is a superposition of pointing up and pointing down, right? So I have a bunch of atoms here. Individually, I don't know each of them what they are doing, right? It could be up, it could be down, but once you do the measurement, okay, some of them go this way, some of them go this way. Okay, so now I have a big, if you are given an explicit formula for the state, then I can calculate the proportion, or how many percentage will go up, how many percent of the beam will come down, because this is a probability, right? So all the atoms are having the same state, but once you measure it, some of them you get this, some of them you get this. Okay, so for this beam, for atoms in this beam, right? We can calculate the probabilities. So probability that after passing the magnet, the atom goes up, is given by the well, this is the probability is what? So this one was still postulate 3, right? Postulate 3 was a very long sentence, and is basically telling us that to calculate a postulate 3, we are given this state, but to calculate the outcome of this, I close this with the up bra and take the modulus square. Okay, so basically, yeah, so now I think by now it's pretty clear how to do this calculation, right? So we've got A up vector and then B up vector and then this. So this times this will get 1, right? But this times this will get 0. So basically what you get is modulus A square. Okay, A can be any complex number, so this is why I put a modulus square, not just A square. Okay, so the same story, probability that atom goes down is P going down, so you do this calculation. Alright, so what does doing this calculation mean? Well, my state is A plus B, so this is A up plus B down, right? So this time this 0, this time this get 1, so I just get B square, B modulus square, right? So this is my probability. Okay, then let's take another concrete example. So just to show you how it's going on, even more concrete example. Okay, so let's say my atom beam is an equal superposition, right? So it's 1 square root 2, 1 over square root 2. So right, this is an equal superposition. Then if I want to calculate the probability of the particle going up, means I do this, right? So for this case, well, is 1 over square root 2 up plus down, right? So this is why orthonormality is very convenient to us, because this 1, the other one you get 0, so it's 1 over root 2 square. So this is a real number, yes. Then the probability of getting this is half, and then you do this, you do the same calculation, right? Same story, everything, and then you also happen to get the same thing, and then you also get half. So for this example, 50% of atoms go up, the other 50% go down. Okay, so that is what we mean by the probability, right? So it looks, at first when we started doing this, maybe it feels a bit abstract, like what's going on. Now you know what is going on, right? So this is the full beam, and then for this example is this proportion come here, this proportion come here. Okay, hopefully that makes sense. Does anyone have any question? I think it's probably time for a break. How do we know the superposition question? No, it's not dumb, because I have not told you. You mean how do you know this? This is also given. For the moment, let's say it's given. Okay, so the given, right? So I should write a comment about this. So the initial state, for us, right? So an arbitrary superposition is given. Like, how do we know is this number, or maybe it could be some other number? I think, yeah, I will work out another example later. Is given. But what is actually happened, right? In real life, there are special methods, experimental procedure to prepare states of chosen A and B. So this is an experimental problem, This is why I don't know, right? So yeah, it's a good question because, in fact, it's a good question because physics student who major in experimental physics is going to spend the whole time like designing an experiment to choose this and to fine tune the A and B, right? So it's actually not an easy thing to do, and it really depends on the engineering and experimental design and all this, like all the smart problem solving situation that you need to bring in to overcome these problems. What was the other question? Correct, yes. But so for, I guess most of us here are theoretical physicists, right? So these are solutions to Schrodinger equation. So theoretically, any superposition is a solution to Schrodinger equation because of the linearity. Yes, they are linearly, yes, it's a linear combination. Correct. Yes, sorry. So we are basically repeating the example in chapter 1. Because in chapter 1 is just to demonstrate how to do the calculation, but now we can link this to a real experiment. Okay. So yes, I mentioned this already, right? So the state that we are talking about is the spin. That's why we give it this symbol. Okay, a spin up and then a spin down, right? Because we are like imagining the spin vector pointing up, and for this case, the spin vector pointing down, right? Or the full long name is dipole moment. Okay, so I guess, yeah, probably, yeah, so I guess this connecting to real life is a big, I believe is a big step in understanding things, right? So this, yeah, so this is why we arrange the chapters in this way. I guess we take a 10-minute break to further digest all the other new things that we have just learned, and when we come back, I will show you how to calculate expectation value. So 10 minutes break and start recording here. What was the other question? Tsuri was asking a more philosophical question. The sphere is completely rigid and no friction. Does it rotate? I guess simple answer, yes. Like in the ideal case, friction and the rigidity is an extra property, right? Whether it rotates or not, whether it's rigid or not, it can still rotate. Or whether it rotates is the, yeah, it's the same, but it's the same, but it can still rotate, but that just gives you conservation of angular momentum. Yeah, so it won't change after we observe, as long as it's in 3D. Yeah, because in one direction you can only go forward and backwards. So yes, as long as in 3D. It's not. Yes, also correct, Kaheng. Spin is the, well, because you were in mechanics, right? So in mechanics, we are talking about, when we are talking about angular momentum, right? The common thing that we did last time was, let's say, a rotating disk. Okay, so rotating disk and then rotate at omega. The vector here is the axis of rotation, right? And then it will tell you the angular momentum. Okay, so this is the vector that is related to rotation, and then of course you get angular momentum. What was it? I omega, right? Moment of inertia omega. So so the angular momentum vector, if you take the classical model, it depends on I times omega, right? And this depends on the size of the object. So for the disk is half mr squared. Okay, so if we take this to 0 size, then it turns out that even if you take this to 0 size, in quantum mechanics, you can still define this vector, right? So you can just say that the limit of r going to 0, right, of this object, right? Then you get this. But so that is the best way to imagine. Okay, so most of the time you might notice that I always give you pictures to imagine is probably only the first few weeks of this course, because we are coming from classical knowledge to quantum. But actually eventually, right, later we need to stop taking examples from classical mechanics, because the quantum phenomena, the set of quantum phenomena is a larger set than classical picture. So we can't imagine spinning spheres anymore, but we can still define two states with observables with eigenvalues. It's all legitimately existing, and is something that we can measure in experiments. Okay, so that is where it whether it's tricky or simple, I don't know, depends on your point of view. Yes, I mean, just to simple answer, yeah, it's a state, but it's not really spinning. Yeah, it's like a point, but and then you get a vector. So nothing is really spinning here, but we still call it a spin quantum number. So yeah, and this is another one of those philosophical questions which we can't answer, so but we don't really need to answer, because we already can handle all these experimental details already, so it's pretty good enough already. Okay, so that is why. Okay, so given so now let us continue. I recorded, right? So let us continue. We should invent a new word. Well, that's why we invented these two symbols, right? That is why we invented these two things here, the Hilbert space and the cats. So now let's continue. Let's say I am given a beam that prepares the state in this form, right? And then we got the measurement here, and then it will split into two possible outcomes. Now we calculate what is the expectation value, or the mean or average. So the expectation value, I think in probability and statistics it's called the expected value, but I think it is essentially the same thing. Okay, and the expectation value of the, so remember the outcome is pointing up and the outcome is pointing down. The eigenvalue is +1, the eigenvalue is -1 here. And another way I just to have something to imagine this is because it goes to the point where z equals to 1 and it reaches a point where z equals to -1. Okay, so my expectation value, if you take postulate 3, the expectation value of measuring the spin, right, is given by well, if I want to measure the spin, how do I get the expectation value? I close this by my bra and ket. So I take my state, I close this to get a number, right? If sigma z is a Hermitian operator, which it is, then the expectation value would be a real number. Okay, so given a state here, let's just do this calculation. Well, it is, let's just plug in everything here. Just we got a bar up vector plus b bar down vector, not vector but down state, and then sigma z, and then a up plus b down, right? So let's see what happens here. This one is still the same for now, right? But this one, if I multiply this inside, a is a number, I can shift it aside. So this times this, I get a eigenstate, come back to the eigenstate with eigenvalue +1, right? And then sigma z times the down vector, I get a -1 eigenvalue down. Okay, so it's this vector times, is this times this. Okay, so I think if you are not used to this calculation, let me go a bit slower and write one more step. So sigma times this is basically a up minus b down. Okay, and then we use it. So this is why orthogonal states are very easy to use, because up times up will give you 1. So I got a bar times a. This times this will get 0, so nothing here. This times this also 0. This times this, I get minus b bar b. So my expectation value is absolute a square minus absolute b squared. Okay, so as you can see, in general, the expectation value, because remember, my state should be normalized. So that means A modular square plus B modular square must be equals to 1, right? Must be equals to 1. So this can either go between between -1 and +1. A lot of sharp corners to write. Right? What is the expectation value? Expectation value is the outcome, right? So it depends on what is the percentage. If 100% of my atom is in up state, then all my atoms are here, so my expectation value is +1, right? If 100% are the down spins, then I get the expectation value of -1, okay? Or if it's a 50-50, right? 50-50 should be somewhere in the middle of +1 and -1, then you get the 0. Okay, so this is where all the statistic stuff come in. Yeah, because I was asking Dr. Gloria expectation value, and then like, what on is actually the expected value. Right, and I think the symbol is probably like E sigma Z or something. Let me increase the brightness. Right, so the and also this is something you learn in probability also, right? The expected value is somewhere inside your sample domain, right? Between -1 to +1. You cannot go beyond that, because the worst is here, the best is here, so what will happen is always from the worst to the best, right? So like this. Okay, just to give another concrete example, let's say all of you take the exam, right? All of you take the exam mark is from 0 to 100, so my expectation value, my average score of the exam should be somewhere between 0 to 100, right? There's no such thing as after taking the exam and then I calculate, oh, the average exam score is -25. Like, how do you get -25? You know, even if you absent is a 0, so there's no such thing. So expectation value should be somewhere within some domain. Yeah, there's a good way to think about this. So so expectation value can be larger than 1, because for that tutorial, your eigenvalues for the tutorial question 2, right? Your eigenvalue is n square, and then the n is from 1, 2, 3. So your eigenvalues are 1, 4, 9. So your expectation value should not exceed 9 and should not go less than 1. So this is for the tutorial question. Okay, so now let's put an example. 2.1.1. Okay, so let's say some smart experimentalists managed to build some perfect machine that can prepare the state in this form. So if I can prepare this particular superposition of state, we can calculate the probabilities, expectation values, and all those things, and let's see how we get it. Right, so this is example 2.1.1. So we have an oven prepares the silver atom beam in the state. So this is some specific form of superposition. √3/2 up plus half down, right? So let's calculate the expectation value of this. Okay, so this is not a balanced superposition. It seems like this is a higher number. Is it a higher number? Yeah, so higher number. It seems like there's going to be more atoms will end up going up, slightly less atoms going down. So let's see what's the expectation value. or expected value. I think the reason why they call it different things, right? Because a lot of things from early quantum mechanics is translated from German. So maybe it came from the German word of expected value, and after going through translation it turns into expectation value in quantum mechanics. But well, let's see what happens to this state. Okay, so these are real numbers, so I turn this into the bra, still the real number, right? And then my sigma z operates to here, right? So the bra, let me keep the same for now. And then this acting on the up state gives an eigenvalue +1. So I got root 3 over 2, still eigenvalue +1. This acting on this, I get eigenvalue -1. Right? Then now I can multiply them. The up and up, multiply them, I get 3 over 2. The rest are negative, but this times this, I get -1 over 4. Okay? So, is it correct? Wait. 3 times this, so this is 4. Right? So 3 over 2 minus 1 over 4, I get 2 over 4, which is a half. Okay? Which is half. So what I get here is that my beam, my expectation, my outcomes, right? So the answer is half, and is it make sense? It should make sense because my outcomes, right? So if my atom is going up, I will get a +1, right? If my atom is pointing down, I will get a -1, is 0. Then my expected value is half over here. So you can see like the probability and statistic intuition comes into play, right? So this has a higher proportion of up and lower proportion of down. So this is why my expectation value is, yeah, so sigma z is half over here, right? Yeah, so this is the down state, this is the up state. Okay, so that was for the expectation values. How about the probabilities? So once you got the probabilities, we can getting one from the other is pretty straightforward. But let's calculate the probabilities. So the probability of getting up, remember how to do it? We just close it with the up vector, and then take the state here, right? So that will give me the so if you remember, it will give me the components corresponding to the up coefficient, right? Or if you do the longer calculation, you just need to do it this way: root 3 over 2 up plus half down modulus square. So it will just pick out the coefficient for this. So it's just root 3 over 2 modulus square. So you got 3 over 4. Right? So 75% probabilities. And then to get the other probability, well, you just need to do this. So it just picks up the other coefficient. So it's half modulus square. So it's just 1 over 4. Or you can also calculate, if you already calculate the first probability, right, then we know that the other probability is just 1 minus this probability. So it's 3 over 4, 1 minus 3 over 4, which is just 1 over 4. Okay, so from here for this state, right, so for this state, we find that the 75% of the beam goes up, and then the other 25% going down. Okay, so the upper beam has more atoms than the lower beam. This is in the superposition state. But again, let me emphasize the weird philosophical weirdness about this. Before passing through the measurement, each atom is in a superposition state. So for any given atom, you don't know whether it's going to be up or down. But for one atom, after passing through this, there is 75% chance to go here and 25% chance to go here. This is why quantum mechanics is not deterministic, it is probabilistic. Because in Newtonian mechanics, a particle will definitely do something with 100% certainty, right? As long as you can calculate Newton's law, everything. But here, we cannot. The best we can do is to get the probability distribution. We cannot predict any more accurate than that, unless it is in the eigenstate. Okay. So now we can, so just to emphasize the concept of expectation value, we can actually calculate expectation value based on the traditional statistics method. Calculate sigma z from traditional methods. Right? So just now I calculate using the bra-ket kind of thing, but if I want to calculate this, well, because this is the expectation value, so it's just taking the eigenvalue of this state and then you times by the probability, right? And then plus the eigenvalue times the corresponding probability, right? So I don't know what's the general or the notation for the statistics expectation value, but it's the value times probability and then value times probability, right? So the probability of +1 is 3/4, and then the getting a probability of -1 times 1/4, so you still get 3/4 minus 1/4, so we're back to half, right? So just like what we got just now. Okay, any question? Oh, I know who you're talking about. Evangelion, right? Eh? Yeah, Evangelion. She's German, I think. Sigma z, just let the phi becomes minus from the sum. What do you mean? Basically just follow the formula lah, right? So the formula, yeah, so the formula, because the reason is because sigma z up is up, sigma z down is negative down, because we are using this equation, right? So we plug in this. Okay. Oh yeah, as you already said it. Yes. So when I say eigenstate, right, I'm referring to eigenstate of a Hermitian operator. Okay, so the up and down are eigenstates of the sigma z. Correct. So why we want Hermitian operator is because we are talking about real eigenvalues, right? So the Stern-Gerlach outcome must be real number, +1 or -1, right? Because we're talking about the z-axis here. Yes, operator up, lambda up. So yes, it's not always plus and -1. It's only for this Stern-Gerlach experiment. So when we talking about other things, then we in the next few chapters we will solve more and more different problems, and we will get different values. Okay, so yeah, so let us what time are we at now? Yeah, so let me re-emphasize what we are talking about in postulate 3. Right? So postulate 3 in the context of Stern-Gerlach experiment. Right? Because postulate 3 is a very long sentence and is very abstract and things like this, right? So what does postulate 3 says? Right? I said just now, before we measure, we don't know. Right? After measure is only one of the outcomes. So I'll just write down what I just said. So it's C up arrow, A plus B down arrow, right? So we don't know the actual state of the atom, so whether it's up or down before the measurement. Right, but if this state we have figured out, we have only calculate the probabilities. Through sigma z. So this is the measurement operator. Okay, so why we want it to be Hermitian is because, yeah, the outcomes are real numbers, so that's why we focus on Hermitian operator, right? We do not have experiment to get complex number outcomes, so therefore we will not use non-Hermitian operators. Okay, so but after passing through Z is either the measurement, right? We get either or, right? So either one of this, but the main point is no longer superposition. Okay, so no longer superposition. So remember that postulate says that measurement of Q will leave the system in one of the eigenstates of Q, right? So that was kind of like what was postulate 3 was discussing when we were talking about it last week, I think. Okay, so yeah, so it leaves it in the eigenstate of Q. So that means what happens if we measure it a second time? Okay, because after measuring there's no more superposition. If it's no more superposition, then if you measure the second time, then you get the definite outcome now, right? So no longer probabilistic. So after you measure, it becomes deterministic now. So let's say I take an oven, right? So it passed through measurement, right? So yeah, so let's say I have some distribution of up, some distribution of down. We don't know, it is a superposition state, right? So so this proportion of the atoms will come here, right? So let me channel this beam and measure this the second time. What's going to happen? What's going to happen is that all of them will go up 100%, right? So nobody will come here. Okay, so if I take the other part of the beam, the same story happens, right? So if initially was in a superposition, you measure this, then there is a certain chance it will getting spin down, right? Spin down. So then this is no longer a superposition, right? It's just everybody is in down, definitely in down. So that means nobody will go up, definitely it will come down 100%, right? So all of the beam will come down. So you see, that is also this experimental setup. Now that we explained the experiment from the beginning, is kind of not so surprising, right? We already know it's up, but if you think about it, that is the philosophical statement. The observation actually influence the state of the particle, right? You are making an observation here. So if you make an observation here, the superposition is destroyed, right? It becomes this. So after you observe the particle, and then there's no more quantum superposition effects anymore, right? So all of them are in the same state coming here, and all of them are in the same state coming down here. Okay, so no more superposition and everything becomes deterministic. Okay, so that is the consequence of measuring something a second time. Is that confusing or too philosophical? Okay, so yeah, so that is the basic idea of the, at least the basic setup of the Stern-Gerlach experiment. So, well, now that we have understand like the basic building blocks, now we can start of play around and do other things. So 2.1.3, selectors and flippers. So this, the main point of this part is just to introduce to you more operators, right, that are not necessarily observables, but operators, remember operator, it eats a vector and spit out a new vector. Okay, so only Hermitian operator corresponds to observations, but there are other things besides observations. So that is what we want to discuss over here. Correct. If you determine the state of all particles, then no more superposition. Yes. So that's a, okay. This is also an interesting question. If we measure some state and then we keep it somewhere after a long time, ideal case it will remain the same. Yes, in the ideal case. So if you do not, so if you, because if it doesn't collide with other particles, or if you don't, nothing happens to it, like in a pure vacuum, then yes, it will remain this almost forever. But that's a problem, because just like a lot of things in ideal case in physics, right? A lot of things is non-ideal. So eventually, like, it will collide with other things and it will interact with other things. So it will somehow become a superposition again if you do not keep it in this state for long. So that is why what Kaheng said just now actually cannot be achieved. If you measure the spin of all the particles, right? But all the particles, you cannot keep them in the eigenstate anymore. It will interact with some system and it will become a superposition again. So that is also a limitation. Yeah, so we preserve particles for, yeah, so that is why, like, storing particles in a certain state is also another challenge. And people in quantum information, like right now, they are working very hard to figure this out, right? To find a way to keep this to preserve quantum states, to preserve coherence, basically. That's the technical term for it, but I haven't talked about coherence yet. Okay, so now we go to introduce to you a new type of operator, which we'll call a selector. Okay, so selector, right, it just is kind of like a filter. So we can imagine a more like everyday language will be, probably I would say, is a filter. So that means given any beam, it selects only the down state or the up states. Okay, so let's say I have the up selector. Okay, so how do you do it? Well, we can easily imagine we can build this from the Stern-Gerlach experiment, right? So let's say so for whatever state this is in, right, some of them will go up, some of them will come down. Okay, so but if I just want the up selector, then all I need to do is I just need to keep this, right? So I just need to keep, so whatever that comes out is just be pointing up, and then this one I just throw away. Okay, so imagine I built some machine to do this. Then this is some device. This is some device. that takes any input of this state, and then this thing, it will guarantee that this output comes out, right? So this is my selector, so I'll just call this symbol S plus, because it keeps the positive one outcome, right? So for any state, any arbitrary state, this thing will come out. Okay, so this is my up selector. Then I can do the same thing with the down selector, right? So any state comes in, I can build a Stern-Gerlach experiment, but I throw away this part, but I will keep this beam. So what comes out is purely going to be all atoms coming down, right? So imagine this is some device, so I put it in a box, and therefore I get this device now that is in a box. So this is the down selector. So any state that you feed it in, the output will guarantee to be down. Okay, so in that sense, this is a simple way to prepare a state, right? Because just now I was saying there's a very complicated experimental challenge to prepare a quantum state in a certain combination, but in a certain superposition, but here I can at least prepare these two states, right? So using a selector, we can prepare, right? So prepare is a very huge word in quantum mechanics because it's a very big experimental challenge. So we can prepare an atom or the beam to be either one of the eigenstates, right? So because in general, something that comes out of the oven, you don't know whether it's spin up or spin down. You need to measure it, but once you measure it, then I can keep the up beam, so then I know the beam everywhere will be spin up, right? Beam everywhere will be spin down. Okay, so this is an operator, because this is an operator, right? Selectors are operators. Okay, because it eats a state, a ket, and spits out either up or down. That's what we mean by operator, right? Or you shit it up. Okay, so but that's how we define our operator in our kind of like non-rigorous sense of Hilbert space. So if it's an operator, then I can write this as a like a mathematical formula. So the mathematical formula, if you imagine what kind of operator that only keeps this vector, well, it's just going to be 1 0 0 0, right? So for this vector, it's just going to be 0 0 0 1. Okay, and in fact, yeah, we have actually shown that this is actually the up ket bra, up ket bra, and this is the down ket bra. Okay, so you guys know how to go. Why is this related to this, right? Remember? If not, you can ask me. We did this before, I think. I don't know how. Yeah, but basically we can see the let's look at the selector operation, right? So let's check how this works. Okay, so let's take an arbitrary state. Psi is to be A up and B down. Okay, so I'll just to be like make sure everyone is used to it and practice our bra-ket. We do it in two ways. So I can write this in bra-ket form, or I can write this in the column vector form, right? So let's say this thing, right, it passes through, let's say, a plus selector, and the output is going to be what? Okay, so the output is going to be S plus operated on sigma. All right, so let's do the matrix multiplication first. So this is 1 0 0 1, right? Hang on, 0, and then this is A times B. So what you get is just A and 0, right? So it's just A 1 0, right? So everything is in up. Okay, but this state is not normalized. Let's worry about normalization later. But for now, everything comes out is going to be 1. Okay, we can do it in the bra-ket form, right? So let's do it in the bra-ket form. So S times this, and what is S in the ket bra? So S times this is up ket up bra, and then the psi. Okay, so yeah, we are practicing how to use this up ket, and then this is the up, and then the psi is A up plus B down. So if I multiply this part will disappear, right? And then I get the A part, I can just move up, up. So up times up is just 1. So I just come back to A up. So these two are the same thing. Okay. So you can imagine doing the similar calculation with the down, right? So imagine any arbitrary state, you do the S minus selector, the output is just the down acting on psi, so you just get the B down. Okay, but yeah, important thing we haven't addressed here. So the output is not normalized. Okay, so we need to normalize this. Shall we? Yeah, let's just normalize this, and so output is not normalized. Let's address this question before we end the class, right? So output is not normalized. Right, so if I take this, right, if I pass through the, let's take the plus selector, so the output, let's call this the phi, right? Phi is the output, and then our outcome, our result was A up. It is not normalized because psi phi psi is modulus A squared, right? If I started with A up, B down, then A mod square plus B mod square is equals to 1, right? So if B is non-zero, then this thing is definitely less than 1. So I need to normalize this. So I need to normalize this. So I'll take this thing, right? Remember the normalization procedure. I just take my original vector that is not normalized and just divide it by the norm. Okay, so phi the norm, and that will give me the normalization. So this was A up, and then mod A square, this thing, so you get plus or minus up. Right, so it's actually up to a phase because this is complex number. Right. So generally it's going to be I theta. It's up to a phase, but the phase doesn't matter. Okay. So if you're not used to complex numbers, those who are not familiar with complex numbers, you should ask me why to get from here to here. But if you're used to it, then I think you know why, right? So, oh, did I draw? Where did I draw the up? Somewhere my drawing is ugly, right? From the, okay, so yeah, okay, so I should answer how to get from here to here. So remember, the thing to remember is A and B are complex numbers, right? So let's take A. So A is a complex number. So a complex number can have, you can either write it in this form, remember lecture 1, or I can write it in this form, right? So in this case, R is x squared plus y squared square root. Theta is the inverse tangent of y over x, right? So a complex number can be written in this form, right? So that means if I take modulus A, I'll just get a R, right? So therefore, if I take A divided by modulus A, is R E I theta divided by R. So it's E I theta. Okay. So this is just an a pure phase. So we call this a pure phase. The reason is because the absolute value is 1. So it only tells us something about the phase. And so, but this time, even if there's an extra phase, it's going to be normalized, because if I take the inner product with itself, right, is basically I need to complex conjugate this and this, right? But they cancel. So pure phase will cancel when you take the inner product. Okay, so the reason is this. Make sense? Right, so now we need to start getting used to complex numbers. Even myself, right? Even myself, I immediately just say, oh, this divided by this is 1, but must remind myself, these are complex number. So complex number, the modulus is 1, but there's this thing there. But actually, okay, even if it's there, it doesn't give us a problem. So just need to be slightly careful. Even if you are not careful, we still get this, then most of the time it's fine. So there's a pros and cons there. Okay, clear? Yeah, so I think, yeah, it's quite late already. So we shall continue. I will introduce to you another operator in the next Monday class. So I think what we plan to do is, unless anyone wants to present in the next week, we will do it in alternate weeks. So we did it this week already. So next week I will just purely lecture everything, unless someone wants to present, and then we figure it out. Okay, yeah, so thanks everyone. Do we have selector in real life? Yeah, so the real life thing I was talking about is, because this is a real life experiment, but basically you just like you just block this beam by you just cover this side with a plastic or something, and then you just let this come out, and then you just so this is the real life selector already, pretty much. You want to present tutorial on question 5? Okay, yeah, we can do that. So tutorial on question 5 for Zirui. Entropy, no, not exactly, no. The reason is because it will go back to superposition state, is because it will interact with other systems, right? So we interact with other system that is uncertain, and can you calculate the entropy? No, actually it's not related to entropy, unless you say that everything that we discuss here have entropy, because everything with a probability you can calculate is entropy. That is the von Neumann's theorem. Okay, so any arbitrary state, A plus B, already there's some entropy related to it. Yeah, this state is going to have an entropy. So in that sense, we already have an entropy before, and then once you get a measurement, you get 0 entropy, right? Outcome 100%, so 0 entropy. But then after you let it, so entropy and superposition is kind of like tied together. They are kind of like the same thing. So yes, you can say it comes back to a superposition is because of entropy, and also because it's the uncertain state. Okay, so wow, chaos is another can of worms. This is not a chaotic system exactly. Chaotic system is a specific kind of uncertainty as well. So yeah, and we won't be learning chaos anytime soon. Okay, so let me stop the recording.